and welcome to this week's Complex Systems seminar that will be about network theory. And I'm Oskar, and these are my fellow presenters.
I'm Andreas.
And I'm Evangelia.
So basically, this presentation will be divided into three parts. We will start to talk a little bit about what a network is and the basic properties of a network. Then we will come into how to model a network. And finally, we will also look at some real-world effects of phenomena that can be understood with the help of network theory. But we will start off with a simple example. So this is Königsberg in the 18th century. Today it's actually called Kaliningrad. And as you see, the city is divided by 7 bridges. So when the people in Königsberg were taking their Sunday strolls in the 18th century, they were discussing, is it possible to devise a path through the city with only crossing each bridge once? And of course this attracted the attention of mathematicians. So in 1736, Leonhard Euler presented a solution to this problem by utilizing network theory or graph theory. So what Euler realized is that it is not important, the paths in the land masses is not important, only the sequence in which you cross the bridges. So he formulated the problem as a graph, or a network. And as you see, we have these nodes representing the land masses of Königsberg, and the edges representing the bridges connecting the land masses. Yes. And what he realized was that every time you come into a node, you also have to leave the node. As you see with these red edges, if you come in here, you have to leave somewhere. So if you want to start and finish in the same node, all the landmasses have to have an even number of bridges connecting to them. And if you want to start and finish in a different node, only 2 of the nodes can have an odd number of bridges connecting to them. And in modern network theory language, this means that the degree of the node, so this is called the degree of the node, these numbers, you see this, the further left has a degree of 5. It has 5 edges connecting to it. So the degree, all the nodes' degree has to be even, or only 2 can be odd. And as you see in Königsberg, all the nodes have odd degree, and hence there is no solution to this problem. So this was in the 18th century, in the first example of using graphs as simplifying a problem and finding a solution. And today, of course, we all know that there is a lot of phenomena that can be explained and simplified in terms of graphs. For example, I'm sure all of you use some social networks like Facebook, Twitter, LinkedIn, or yeah, there are numerous. This is an example of flight routes represented as a network in the world. This was actually used to try to predict the probability of an Ebola outbreak. We also have artificial neural networks, which is of course important for understanding intelligence and how the human brain works, the consciousness and that kind of stuff, and also as an inspiration for artificial neural networks that we have previously worked with. Distributive networks, for example, the blood vessels of the human body. And this is a network representing the World Wide Web, quite complex. So these are just a small variety of examples. There are, of course, very many situations where networks can be used as representations. And now we will have a look at some of the basic properties and characteristics that many of these networks share. And this will hand over to Andreas.
Yeah. So many people have an intuitive view of what a network is. And as such, most probably notice the most basic parts of a network being the nodes and the edges, which Oskar previously talked about. And in a very basic network, all of these are the same. So all the nodes represent, for example, in the case of the Königsberg, a landmass, and all the edges represent a bridge. However, once we want to make some more complex networks, we can change the properties of these parts of the network. For example, the nodes, you could assign them to represent some quality, like nationality or gender or age in a social network, or countries in a geographical network, or web pages in the internet network. And depending on how we assign these, we can divide up the network into different regions of similar traits of the nodes. And likewise, the edges, we can also assign different properties. For example, if we have a social network, the edges could be the friendship between two people, or if we have a citation network of citations, it can be whether one node has cited the other or not. And related to this property, we also have the directionality of the connections between nodes. For example, in the case of the social network, the way you traverse the edge actually matters, because one person must also be a friend with the other. So it doesn't really matter which way you travel, because both are friends with each other. But with the citation networks, just because you have cited someone else does not necessarily mean that they also will cite you, meaning that the direction that you traverse the network actually matters, because you cannot go both ways all the time. And then looking at the bigger picture, where we observe the network as a whole, we also have some properties that are very important for how the network will behave and how we can traverse the network. And the first of these ones I'm going to talk about is the degree distribution of the network. Because like Oskar also mentioned, each node in the network is assigned a degree based on the amount of edges that connect to each node. And once we have a very large network, it doesn't really matter if we talk about the degree of a single node, but we're more interested in the degree distribution across the whole network. And for example, if a network has a few nodes with very large degree and many nodes with very low degree, or if all nodes have a fairly equal degree, it makes a huge impact on the behaviors of the network. And some effects that are caused by these kinds of degree distribution is the small world effect, which many of you probably have heard in the shape of the 6 degrees of separation, meaning that in the real world, each person can be linked at the maximum of 6 steps of mutual friends. And the small world effect, like it says here, is exactly this property, that even in a very complex networks, there are usually paths that you can take through the network, so that even very distant nodes can be connected in only a very few amount of steps, meaning that a large network is connected via a lot of shortcuts through the network. And related to this is the clustering of a network, which also arises from how the degree distribution, where you have a lot of hubs with a high degree in the network. And to illustrate this, I will use this example, which is from a survey in an American school, where the students were asked who were their friends. And after everyone had been asked, they plotted the answers as a function of people were grouped based on the proximity of how many friends they say they had. So close friends of people who had a lot of friends in common were put together in groups. And in this example, there were quite a visible division between ethnicity in the left and right direction, with the white children mostly being friends with other white children and black children being mostly friends with other black children. But also in the age group, whereas at the bottom we have younger students and in the top we have older students. And it's very clear how this network then comes together into 4 main clusters with only a few outliers outside of it. But how do we get these kinds of networks? Evangelia will now describe to you how these networks are different from the basic random networks that were used at the start of the network theory.
Okay. So, no problem. So far, we've seen that all these networks have millions or even billions of nodes and links between them. And that actually makes it really hard for us to say anything about their structure just by looking at them as a graph. So how do we analyze them? We actually create models of networks and then try to find statistical properties that can characterize their structure so that we can actually make predictions about them. So the first type of model I'm going to talk about is the random network. It's this one. And it was actually proposed by 2 Hungarian mathematicians, Andreas and Lilja. And it is random in the sense that, given this set of nodes here, the links between them, it's formed independently of each other with a certain probability. Now, if we look at the degree distribution of a random network, we can have a look at this plot here. So in the x-axis, we have the degree, the possible degrees that we can observe. And on the y-axis, we have the probability to observe this specific degree. Now we see that the random network has this kind of bell-shaped curve as a distribution. And this basically tells us that the majority of the nodes has an average degree. Now, if we think about it, this doesn't sound very realistic. Take, for example, a social network, and imagine that you're a node in this network. How would you make your connections? Would you choose randomly your connections, your friends? Or you would prefer to connect with people you already know, or friends of your friends, for example? And this kind of thinking brings us to another type of structure. This is called the scale-free network here. And this network has 2 main concepts, or these things. It has a few nodes, these blue nodes here, that are actually really important for this network, because they have many links. And we call them hubs. And this can also be reflected in the distribution. For example, these hubs here correspond to this node tail. And at the same time, the rest of the nodes have really few links, which correspond to this kind of peak here. So a scale-free network is more realistic than a random network if we want to describe real-world systems. But still, there's something we need to keep in mind. Like, networks cannot be static. That means that they evolve in time. For example, think about the World Wide Web. Like, each day, new websites are being created, and those who have many links are more likely to get linked again. Or, for example, think about citations. Like, each day, scientists publish different papers, and normally what happens is that papers that have already been cited before are more likely to be cited again. And this kind of examples makes us think that we want to have a model that actually captures this characteristic, that popularity is attractive. Now, before doing that, how can we generate this model? We can go back in time and look at the Bible. And actually, this kind of phenomenon is not new, because it was already mentioned by Matthew in his Gospel. He's actually stating that for whoever has will be given more. And in other words, that means that the rich get richer. Or that nodes that have already made links are more likely to get linked again. And this type of model actually was proposed by Barabasi and Albert in 1999. It's called preferential attachment model. And we're gonna see, okay, it is based, as I mentioned, in two concepts. The first one is that we have this kind of growth. The number of nodes change in time. And the second one is that these nodes are not linked randomly, are linked with a certain bias. If we look at this algorithm, it's very simple. We can start with a small number of nodes, let's say, for example, 2. And then at each step, we add a new node, but we do it with a certain probability. For example, the probability that a new node will be added to an I node is proportional to the degree that I node has. For example, we can look here at this step. We have 3 nodes, right? The node here in the middle has degree 2 because it has 2 links, while the rest of them has degree 1 because they have only 1 link. Now in the next step, the node that we will add will be more likely to get a link, let's say, to the one in the middle. And this is what actually happens. But we should keep in mind that it's a probabilistic model, and this doesn't mean that happens every time. But it's highly likely, and as you imagine, as the higher the degree a node has, it is more likely to get linked again. So if we generate and keep iterating, we will have a network that looks like this. And this is the scale-free network I was talking before. And from that point, actually, there are many really interesting effects that can arise. And Oskar is going to talk about them.
Okay, some of them anyway.
Yes, some of them.
So, now we have covered the first two sections, a little bit about the general properties of networks and how we can model a network. So now we are coming to some of the real-world effects and phenomena that can be maybe understand with the help of these models. So we'll talk mainly about the majority illusion and the friendship paradox. So the friendship paradox basically says that most people, on average, have less friends than their friends have. And this is something that arises from the fact of scale-free networks. Some of the nodes have a lot of connections and some less. It might, for some people this is intuitive, for some it's not that intuitive, but this is something that arises from the scale-free properties of networks. So, and can this be used to understand some phenomena that we can need? And for example, in vaccination policies, imagine that you were to set up a vaccination policy and you only have a limited amount of vaccine. Would you randomly vaccinate people? Is that the most efficient way to do it, or is there a better way? So if you take a look at this scale-free network, so if we randomly vaccinate people, we would assign the same probability to each of these nodes for a vaccination. If we instead would apply an algorithm that said, instead of vaccinating random nodes, we vaccinate random friends of random nodes, then we will have a much larger probability of hitting the hubs. And this can also be used, for example, in monitoring contagious outbreaks. It's the same principle. Instead of, you cannot monitor everyone, and instead of monitoring random people, you would want to monitor the people with a lot of connections, of course. And this, and maybe it's easier also to look at it like this. For example, if we have a really simple extreme case network, so here we have 10 nodes, and one node has a lot of friends, the other is a bit, they only have one. And if we would choose nodes randomly here, of course, we would have 1/10 of choosing every node. But if we would choose random friends or random nodes, we would have 9/10 probability of choosing this node. So this effect is clearly seen in this extreme example also. And actually, the friendship paradox can be generalized to any property correlated with the degree of a node. For example, citations that we heard about earlier. And also, it might be helps understood the emergence of social norms. For example, why does some social norms in a society get a hold on the people and spread, and some does not? So this modeling of used to understand contagious behaviors in the extension. So, and this is the next topic that Andreas will talk about.
Yes. So very much related to the friendship paradox, it is an effect which is known as the majority illusion. And this is a property of a network in which the opinions or behaviors of a minority of the population of the network to the people in it appear to be actually be the opinions of a majority. And this might be a bit hard to grasp, so like I'm also going to show it in this way. Take these two networks. The connection in both cases is equal. All the connections between nodes are the same. However, in the left network, the red nodes have positions as hubs in a scale-free network, whereas in the right one, the white ones are the hubs. But the large important difference that this makes is that in this left network, if you count, if you list the friends of each node, all the white nodes have a majority of red friends in their, or red nodes connected to them. Whereas in this one, they have all mostly white nodes in their friendship circles. And the consequence of this would be that, for example, if we take a real life example of being that, well, these red nodes can be have like politicians or someone with a lot of opinions, then this entire network where the red people have one opinion and the white one might have another opinion, all the white ones would think that the red opinion is actually the majority, despite there being a vast majority of white node opinion in the network. And this can create a very skewed view of reality. For example, if we take risk behaviors or something like that, if the red nodes are, I don't know, they could be known to be heavy drinkers, then the white nodes might think that, well, it's socially acceptable to be a heavy drinker, despite there being a lot of white nodes who are not actually heavy drinkers. So that's a very basic properties that can emerge from the majority illusion. And like I started with, also political opinions. If these red nodes are very active on Twitter, they will be the people that people hear from, despite them being the minority. And their opinions would be very likely to spread throughout this network of nodes. So that about concludes our talk about some of the real life applications of network theory and their consequences. So would you like to summarize our talk today?
So, okay, in this presentation, we introduced some really important properties that real-world networks share. And then we saw two different types of structure that they can have. And we concluded that if we want to model a real-world network, we probably need to have in mind that we should use a scale-free network. Now, then we actually saw a model that generates this type of network, which is the preferential attachment model. And then we saw also two different, let's say, effects, the friendship paradox and the majority illusion. And from these two different effects, we can actually use them to make predictions about how social norms are created, or opinion dynamics, and so on. And now we're gonna
Yeah. So these are, we will also list some references that if you were interested in our small talk here about network theory, you can have a deeper look into these subjects, the friendship paradox and school integration and also immunization strategies. And actually, as you see, this article about the majority illusions is quite new. It came in June in 2015, so the subject is quite, yeah, you can find new ways to apply this kind of thinking. And yeah. So, is there any questions to us about this talk? Now is a good time to ask them. Okay,
So
then thank you.
You can say the questions to the discussion session. It's
Yeah, just about if they have any question about the presentation.
oh yeah. That makes sense. It can just be part of the limit if there is something. But in any case, that's so you are through the presentation.
Yeah,
Yes.
thank you.
Thank you very much.
So then our fellow review group has it's listed a few questions here.
Claes, du har en.
Ja.